Let's look at my next example. It asks me to identify the quadrant or quadrant of any angle theta that satisfies sine theta less than 0 and secant theta that is less than 0. Let's recall that sine theta is equal to y over r. And what we need to do is to take a look at a coordinate plane and determine where sine theta is going to be less than 0. Or, in other words, my y value has to be negative. My r value is always positive. So if we take a look at a coordinate plane, the two locations where my y value is negative is going to be in quadrant 3, where my x value is negative and my y value is negative. And in quadrant 3, a negative y over a positive r gives me a sine theta that will be less than 0. Another quadrant is going to be quadrant 4. Here, a point on my terminal side is going to have an associated x value that is positive, but a y value that is negative. And this will give me a sine theta that has a negative y over a positive r that represents sine theta to be less than 0. So the two quadrants that satisfy sine theta to be less than 0 are going to be quadrant 3 and quadrant 4. Let's take a look at secant theta. We know secant theta is the reciprocal of cosine theta, which is x over r. So secant theta is r over x. Well, let's take a look at a coordinate plane and identify quadrants where my x value is going to be negative. That will represent quadrants that have secant theta less than 0. Those two quadrants are going to be quadrant 2, where my x value is negative and my y value is positive, and quadrant 3, where my x value is negative and my y value is negative. In both of those quadrants, I'll have x negative and an r positive, and when I divide, I'll have a negative value. That'll represent secant theta to be less than 0. These two quadrants that solve this half are going to be quadrant 2 and quadrant 3. Now, if I combine the two constraints, on the first one, 3 and 4, and the second one, 2 and 3, the only ones that where sine theta is less than 0 and secant theta is less than 0 is my final solution, which will be quadrant 3. Let's take a look at the next topic in our section, which is ranges of trig functions, that is the y values. And what we want to do is think of a circle with a radius of 1. In the diagram shown, we already have a radius in there, or an r value equal to 1. And what we want to do is generate more angles inside different quadrants and see how small or how big our y values get depending on where this angle is located, whether it's in a specific quadrant or it is actually a quadrant angle. And from this, we're going to find out what is the range, the high or the low, inside of a trig function for its y values. The first angles I want to look at are the quadrant angles. So let's start by taking a look at an initial angle at degree 0. In this situation, I have an x value of 1, but my y value at 0 degrees is 0. My next one, going counterclockwise, would be generating an angle at 90 degrees. In this situation, I have an x value of 0, but here my y value is 1. Continuing counterclockwise, I'd head to 180 degrees. Here, similar to my 0 degrees, my x value is going to be a negative 1, but again, my y value is 0. If I go to 270 degrees, I'm going to have a situation where my x is 0 again, but here my y value is a negative 1. So you can see at this point so far, my range seems to go from small to large to be a negative 1 to 0. And it looks like it's going to continue that way even if I use the terminal side of this angle already generated. And notice that my my y value is going to be less than my one that's already generated at 90 degrees. I can continue this process and demonstrate that my y value will never be as big as it was until it gets to be 90 degrees. They either increase till they get to 1 at 90 degrees, but they're not quite 1 till they get there, and they decrease as they get greater than 90 degrees. As a matter of fact, they decrease down to a point as I continue down into my third quadrant until they get to actually 270 degrees, where my y value is a -1. And then they start to increase again as I approach back to 0 and head toward 90 again. So in this situation, my range is going to fall between a -1 and 1. Now we have to determine is, well, what functions are going to have that range inside my 6 trig functions. Keeping the previous slide in mind, we want to take a look at what is shown on this slide, which is the true ranges of trig functions, that is the y values. And what we did determine is for any angle theta for which the indicated function exists. I recall some functions are undefined at certain locations throughout the coordinate plane. But what we did determine on number 1 on the previous slide was that I have a sine theta, which will give me a y value, and an x theta will give me an x value, is going to give me a range on sine theta between a -1 and 1, and similar for cosine theta. Tangent theta and cotangent theta can be equal, can equal any real number, and also I like to see where number 1 relates to number 3, since sine and cosine are between -1 and 1. Secant and cosecant are the exact opposite, where secant theta has to be less than -1 or greater than 1, and also for cosecant theta, which is less than a -1 or greater than 1, since they are reciprocals or opposite of my sine and cosine theta. Notice that secant theta and cosecant theta are never between a -1 and 1. The last topic in this section is identities. We have 2 different types. The first one we're going to start out with is Pythagorean. And the other one is the quotient identity, which is sine theta over cosine theta, which equals tangent theta. And the last one is cosine theta over sine theta, which is cotangent theta. And those are reciprocals of each other. Let's continue with an example based on these identities. The first example for function values. Number 1 says find sine theta and cosine theta if tangent theta equals 4/3. But your constraint is theta is in quadrant 3. The first bullet point down here, since sine theta is in quadrant 3, sine theta and cosine theta will both be negative. Recall that's true because in quadrant 3, if I have an angle, my x is negative and my y is negative. So sine theta and cosine theta are y over r and x over r. So negative divided by positive, those values will both be negative. The next bullet point says sine theta and cosine theta must be in the interval between -1 and 1, which is the range we just found in a prior section. To start the solution for this problem, we need to look at where we're starting at, which is tangent theta, and use an identity that is going to get us toward a sine theta or cosine theta, or at least one of the reciprocal functions, a tangent related to either sine, or in the other case, a reciprocal or cosecant theta, or a tangent related to a cosine or a secant theta. So let's go back a page and take a look at the identities. On the right, the quotient functions look like they're going to work, but they have all 3 in there, sine, cosine, and tangent, which are here. And of course, we don't want to bring in a cotangent because that's not part of our problem. The first Pythagorean identity shows sine, cosine, which is very like it has a chance, but we're still dealing with a tangent theta. On our second one, they do give us a tangent theta, and they give us a secant theta, which we know secant is the reciprocal for cosine. So if we can find out what secant is, we can find out what cosine is. So I believe this is the identity we need to use to solve for this problem. So let's utilize that identity. So this is the procedure I'd like you to use. Always copy the trig identity and then substitute in so we get an idea what these trig identities look like on a constant basis. So what we want to do is copy the trig identity that we discussed earlier, which is tangent squared theta plus 1 equals secant squared theta. Tangent we already know, so that's why we use tangent squared theta, and secant squared theta is the reciprocal for cosine. So we can find our value for cosine once we know what secant is. So let's just substitute in and try to simplify this problem. So when we substitute in for tangent theta, we're going to get 4/3 squared plus 1 equals secant squared theta. Continuing, we square 4/3 and we get 16/9 plus 1 equals secant squared theta. Find the sum. 16 over 9 plus 1, or 9 over 9, is going to give us 25/9. Take the square root, and that's going to be 5/3. But recall, cosine and sine are negative in quadrant 3, which was a constraint in the original problem. Therefore, if sine and cosine are negative in quadrant 3, so are their reciprocals, secant and cosecant. Now, once I know that secant is a negative 5/3, all we need to do is find the reciprocal, and I get a negative 3/5. Let's continue the problem and solve for sine. We're going to use the Pythagorean identity sine squared theta plus cosine squared theta equals 1. We want to solve for sine, so we'll subtract cosine squared theta on both sides. Then substitute in for cosine, which is a negative 3/5. Square it, we'll get 9/25. We'll subtract from 1 and get 16/25. And then take the square root of both sides and get 4/5. But remember the constraint that we're in quadrant 3, and sine is negative in quadrant 3. Your assignment is given, and what we need you to do is refer to the discussion board if you have any questions.